another one of these really classic concentration of momentum problems. Looks like this. There's a bullet here which has a mass, which I'm going to note by little m, moving at some speed v, sort of towards a big wooden block. So there's a big wooden block here sitting with a mass m. So just imagine, if you can, firing a gun into a wooden block, like a big tree trunk or something like that. So what happens then is the bullet then embeds itself into this piece of wood. So there's the bullet there now stuck in the piece of wood, and the whole system moves out with some speed v, like this, towards the right. So that might be something plausible. You have this big piece of wood sitting here not moving, but if you fire a bullet into it, not only will the bullet embed itself into the block, but the whole system is going to move off to the right after the collision occurs. The other thing that the problem states that you have to be sort of very careful about is that this is a wooden block on a wooden floor. And whenever you get clues about structure like that, then you have to assume that there's some use of kinetic in here, some kinetic coefficient of friction in there, which if you look up in your book is something like 0.5. So there is a coefficient of friction between this block here, which has a bullet in it, and the wooden floor. So it's going to slide along. I think it says something like, how long does it take the block before it's going to stop or something like that. But in either case, whatever the problem is asking for here, it's going to be very important for you to figure out what this final v is right here, because whether it's asking for a stopping distance, which you can find from using equations 1, 2, or 3 from the very first week of class, or they back it out, they give you the distance and want to know the speed, you have to have some relationship which tells you what this final speed is of the wooden block bullet blob as a function of the initial conditions here. It's quite straightforward to find. Let's try an approach like this. Why don't we try conservation of energy? We can say E initial is equal to E final. And so what initial energy do I have? Well, I have the kinetic energy of the bullet there, 1/2 mv squared, and when I'm all done, I'll have the 1/2 the kinetic energy of the block bullet blob moving together. Now I sum the masses because the bullet is embedded in the block times v squared, something like that. So it looks like the 1/2s cancel, and I can solve this thing for capital V, and it'll be the square root of something that you can sort of solve for. Okay? So that seems like it would give me the speed of the block bullet blob after the collision. It does seem like it would, but this approach is entirely wrong. The reason why it's wrong is because energy is not conserved in this process. I agree that the kinetic energy of the bullet probably has something to do with the final kinetic energy of the block bullet blob after the collision, but energy is lost when the bullet embeds itself in the block. And so the energy process does convert this kinetic energy. Some of it goes into the kinetic energy of the block bullet blob after the collision, but the problem is that some of the energy leaks out. So if you draw a big arrow like this, some of the energy leaks out here. We'll call it E sub drill, which is the energy that's lost when the bullet drills itself into that piece of wood. So you can't have that available to you in terms of straight concentration of momentum. You could, concentration of energy. You could if you wanted to, but you'd have to do something like add in the energy of the bullet drilling into the wood over here. This would be a valid equation which you could use, but you have no idea what this is, and you have no way of finding that out unless you go into a laboratory and measure energy loss and stuff, which we're obviously not going to do. So energy is just not the way to approach this. So the only way to approach it then is momentum. Momentum still will be conserved even with that drilling process happening here. So it's all on the x-axis. So I can say P initial x is equal to P final x, something like that. Now what do I have moving initially? The bullet. There's the momentum of the bullet right there. And the block is not moving at all before the collision. It has no momentum, so there'll just be a big zero here for the block. And after the collision's over, I do have the sum of the two times its outgoing speed. And so this relation right here, this gives me the relation that I'm looking for here. The speed of the outgoing blob as a function of all of the other parameters. There's the bullet speed right there. There's the two masses of the two. This is the proper equation here for the outgoing speed of this block. Now the problem could ask you a variety of different things now. Since there is a coefficient of friction, you would imagine this to be a rough surface, but in either case you're in really good control of the problem to solve for whatever they're asking for because you know what the speed is of the outgoing block bullet combination here. If they want to know the stopping distance, you could say something like v squared is v naught squared minus 2a times delta x, because what will happen is as soon as the block bullet blob starts to move that way on the friction surface here, there will be a frictional force which is going to oppose that motion back the other way. So you're sort of back into a problem that we've done a couple weeks ago, sort of a one-dimensional kinematics problem, where of course the frictional force is mu times the normal force. In this case, that mu is going to be mu and then m plus m times g. This will be the frictional force on it. You can divide by the mass of the block to find the acceleration or whatever the case may be. But these velocities right here, like the initial velocity of the system after the collision, is this big V. So that's how fast it would be moving after the collision, and you might very well be interested in it coming to rest at some point. So this equation could be adapted to be something like, well, it comes to rest when the final speed is equal to 0, given that it left the collision with this big V, which you can find right here, and then you can have the minus 2a times delta x on it, where the a is, of course, related to the frictional force. Something like the frictional deceleration then would be the frictional force divided by little m plus big M. You know, some combination of things like that, but in either case, it is just reduced down to a kinematics problem. You have a frictional deceleration, but the core of the problem really is, again, this outgoing speed of the bullet blob as a function of all the initial parameters here, and also hopefully you can get the idea in your head here that using E initial equal to E final just isn't going to work here, because you lose a bit of energy when the bullet embeds itself in the block, so you can't expect to have that energy available for motion. So that's the way that problem will come out.